Okay, so thanks a lot, Matt, and thanks a lot for coming. So what I'll talk about today is semi-definite programming and polynomial optimization. And part of what I'm going to present, especially the second part of this talk, will be joint work with James Saunderson, who is at Monash University in Australia, and Pablo Parrillo at MIT. Okay. So I'd like to start with something that I think most of you, if not all of you, actually know. I mean, this is something that is really used heavily in industry, which is linear programming. So linear programming is a class of optimization problem that looks like this. So it's essentially the minimization of a certain linear function subject to linear constraints, subject to linear inequality constraints. So it's probably the simplest class of optimization problems that you can think of. Okay, but this class of optimization problems has really many applications in industry. It's used in virtually all different sectors of industry: energy, transportation, healthcare, finance, etc. Whenever you have scheduling and planning or design problems. Okay, so maybe I can mention some history about this linear programming. So this, I mean, George Dantzig, who's pictured here, is one of the founders of linear programming, somehow one of the persons who realized the importance of such optimization problems. Okay, and he actually developed this theory of linear programming when he was working for the military during the Second World War, so in the 1940s, at the end of the 1940s. And since then, the theory of linear programming has progressed immensely, and solvers have progressed also immensely, and now we can solve problems with really a large number of variables. I mean, tens of thousands, hundreds of thousands of variables, and as I mentioned, this is really used in many different applications. I mean, so the simplex method, which George Dantzig has invented, is usually considered one of the top 10 algorithms of the 20th century, along with FFT and other very well-known algorithms used in numerical simulation and so on. So just to, I mean, I've put this picture, so just to give you an idea of what is the geometry behind linear programming. It's again a very simple geometry. So you have a certain feasible set that's called a polyhedron, okay, in geometry. So that's the set defined using linear inequalities. And what you want to do is to essentially optimize a linear function given by a linear cost vector. So this is C. So essentially you want to move upwards as much as you can while staying in this feasible set. And so in this case it would be this would be the optimal point. Okay, so this is essentially a very simple geometry, but extremely powerful one. Okay, so what I want to talk today is about actually a generalization of linear programming. So a much more recent class of optimization problem that is called semi-definite programming, and that contains linear programming as a special case. Okay, and this is what I call semi-definite programming. So this is what people call semi-definite programming. Okay, so before I introduce semi-definite programming, I just need to remind you something from linear algebra. So whenever I take a symmetric matrix, okay, this symmetric matrix always has real eigenvalues. Okay, and I'm going to call a symmetric matrix positive semi-definite if all its eigenvalues are non-negative. Okay. So maybe I can just to connect with people who are far away from linear algebra. I mean, positive semi-definite matrices show up typically when you consider covariance matrices of random variables. So if you have a set of random variables and you form the covariant matrix, that's always a positive semi-definite matrix. Okay. So what is semi-definite programming? So semi-definite programming looks exactly like a linear program, except that I've changed now this inequality sign here with a curly inequality sign. Okay, and the curly inequality sign means that a of x minus b now is positive semi-definite, meaning that a of x minus b has non-negative eigenvalues. Okay, so A is a linear map that takes a vector and outputs a symmetric matrix. Okay, and the feasible set is then given by the set of x such that a of x is bigger than b. Okay, the feasible set is not a polyhedron anymore, so it can have certain smooth parts. So in general, the feasible set will be still a convex set, but the boundary will be piecewise smooth instead of just being polyhedron. Okay, so it can have so you can have smooth parts here as well as more pointy parts in here. Okay. So why do we care about semi-definite programming? So semi-definite programming, by extending the theory of linear programming, people have realized that we also have efficient algorithms to solve these kinds of problems. Okay, so now you may ask, such problems are very natural to, so they appear very naturally in applications. I mean, maybe I can mention one of the historical applications, probably one of the first problems that was solved in linear programming to test the simplex method was the famous diet problem, where essentially the military was looking for the best way to essentially feed their soldiers in order to guarantee that they have a sufficient amount of vitamins and other other the nutritional components. And so essentially they wanted to minimize the cost of buying all this food, subject to making sure that they have the sufficient amount of vitamins and so on and so forth. Okay, so linear programming shows up naturally. Now you may ask why, I mean, where in practice would I find, yes, positive semi-definite matrices, and why would I want to impose such constraints? Okay, so and what I want to try to convince you today is that such problems are really very important. Okay. So I mean, first, I mean, just to get some intuition about what semi-definite programming is. So let's actually just think of a very simple problem and assume that you have a certain design variable. So let's say it's just 2 dimensions, just to make things simple. You have x and y, and you want to encode that x squared plus y squared, so some kind of energy is less than 1. Okay, so such constraints you cannot impose using linear programming, because this is obviously not a polyhedron. Okay, and yet this you can encode. So this is a simple exercise. You can show that this is true if and only if this 2 by 2 positive semi-definite, this 2 by 2 matrix is positive semi-definite. Okay, this is a simple computation of determinant. Okay, so this is one example where you can do something interesting that linear programming doesn't do. So another case is if you want to have a rational function. So say you want to say 1 over x, the simplest rational function, is less than t. You want to impose this constraint in your program. Then you can also do this using semi-definite programming. You just impose this 2 by 2 positive semi-definite matrix, this 2 by 2 positive semi-definite condition. Okay, so these are nice kind of applications, I mean, constraints that you can impose using semi-definite programming that you cannot do using linear programming. But what I want to talk today about is more about actually the real power of semi-definite programming. And this is the second kind of part in the title of my talk, which is to tackle really polynomial optimization problem, really arbitrary polynomial optimization problem. And what I want to describe in the 2 or 3 slides next is this following machine here that you see, which is called the sum of squares relaxations. So that's a general way of taking any polynomial optimization problem, possibly non-convex. So essentially you want to minimize a certain polynomial subject to polynomial constraints. Everything can be non-convex. Okay, you put it inside this machine called the sum of squares relaxation, and this will output a certain semi-definite program, which is a convex optimization problem that we can solve efficiently, and that will be a good approximation of this. Okay, so what do I mean by good? So this I will try to explain a little bit, but this is actually a subject of still a subject of research. Okay, so how do we actually do this transformation? And this is really one of the real powers of semi-definite programming, and this is an active area of research. And this is essentially my area of research, what I work on. Okay, so maybe let's actually start with the simplest polynomial optimization problem that you can think of. Okay, so you want to minimize a certain polynomial p of x subject to x living in Rn. Okay, polynomial optimization problems are very difficult as soon as you have a polynomial p of degree 4. Okay, you can essentially encode many difficult combinatorial optimization problems as polynomial optimization. So in fact, even just deciding if a polynomial p is non-negative on Rn, even just this decision problem is very difficult, and you can see that this decision problem is essentially saying that the minimum is non-negative. Okay, so this is very hard. So what is the main idea of this sum of squares relaxation? It's a very simple idea that actually goes back to a long time ago, to more than a century. I mean, to work of Hilbert and so on. Is to realize that there is another way to, there is one way to efficiently check if a polynomial is non-negative is to try to write it as a sum of squares of other polynomials. Okay, so if I manage to write p as a sum of squares of other polynomials, okay, then I have a proof, I have a certificate that my polynomial is non-negative. Okay, so I have essentially answered this question. Okay, and the main observation now is that deciding if p is a sum of squares of other polynomials, this is essentially a semi-definite program. Okay, so you can encode this constraint p is a sum of squares as a semi-definite program. So in terms of this, a certain curly matrix A bigger than B, which I'm not going to detail here, but maybe I can just mention one aspect of why one should expect that this decision problem is essentially a sum of squares. So and maybe here I will use some technicalities. So please forgive me if you're not if the vocabulary I will use is not totally fresh. So essentially what you see here, what you have on the right hand side here is a quadratic form. Okay, so and where the qi of x, you can think of the qi of x. These are essentially linear functions. If you think so, these are linear functions of the vector of monomials of 1x, x squared, and so on. Okay, so and essentially a positive semi-definite matrix is nothing but a generic quadratic form, a generic sum of squares. Okay, and so by essentially composing a generic positive semi-definite matrix or a non-negative quadratic form with this map, this nonlinear map that takes a vector, so the x and outputs 1x, x squared, etc., you essentially manage to write P as a sum of squares. Okay, so this is the main idea. Very, I mean, kind of a vague explanation, but this is where it comes from. I mean, this is why deciding if P is a sum of squares is essentially a semi-definite program. So now we may ask the question: is it true that any non-negative polynomial can be written as a sum of squares? Okay, and again, as I mentioned, this problem has been considered by Hilbert a long time ago. In fact, the answer to this question is no in general. I mean, it's true in some very specific cases, but in general, it's going to be no. And so now, since this work of Hilbert and there has been a lot of research in trying to understand the discrepancy between polynomials that are sums of squares and non-negative polynomials. But maybe one thing that I should mention is that actually, in practice, for most polynomials that arise in practice, this kind of relaxation that we get is actually very good in practice. It gives us very good results. So now, I mean, this just gives us a way to decide if a polynomial is a sum of squares. Now, how do I actually use this to do optimization? If let's go back to our original problem, I want to minimize P of x. How can I do this? So the idea is just to observe that if I want to minimize a certain polynomial, let's say this curve here, this is the same as maximizing gamma. So gamma is this line, maximizing gamma such that P minus gamma, such that this polynomial minus this line is still non-negative. Okay, so if I replace the non-negativity constraint by a sum of squares constraint, essentially I get a way to approximate the minimum of my polynomial. Okay, so essentially this problem, find the largest gamma such that B minus gamma is a sum of squares. This is a semi-definite program, and this approximates the minimum of my polynomial. Okay, so this was for probably the simplest polynomial optimization problem. Now you can think of what if I have a generic polynomial optimization problem. I want to minimize a certain polynomial subject to polynomial constraints. So G1 up to Gk are all polynomial. Okay, and again now, so we again go back to the idea of how do I certify that a polynomial P is non-negative on this set. So this is called a semi-algebraic set. So one way to guarantee that a polynomial is non-negative is to try to write it as a sum of squares plus another term here. This is a S1 up to Sk are also sums of squares. So these are obviously by construction non-negative times G1 up to Gk, and G1 up to Gk are non-negative on the set that I'm interested in. Okay, so if I manage to have such an identity, then I am sure that P is going to be larger than gamma on this semi-algebraic set. Okay, and so by maximizing gamma subject to this constraint being satisfied, I get essentially a lower bound on my polynomial optimization problem. And again, what is key here is that solving this optimization problem, essentially finding the largest gamma such that this is true, this is a semi-definite program that we can solve efficiently. Okay. So this is essentially the kind of what I wanted to. This is a kind of a short explanation of what lies inside this machine. Okay, so there is of course a lot of things happening inside here. Studying essentially the quality of these approximations. Okay, when do I actually get the exact value? And whenever I don't get the exact value, essentially what people have devised is a way to construct a hierarchy of semi-definite relaxations. So larger and larger semi-definite relaxations that converge to the true optimal value. Okay, and these are based on results from real algebraic geometry called positive Stellansatz and so on. Okay, so that I will not mention. So are there any questions about this first part of the talk, which was more of an overview of this area? If not, I will. Yes. Please.
So finding the minimal value, how to find the minimum then?
How do I find the minimum? Yes. So okay, that's a good question. Yes. So if it is so by solving this semi-definite program, and by getting the matrix X, which is a positive semi-definite matrix, you can check whether you've actually solved the original thing here. Right, so you essentially, if it's rank 1, you can extract the minimum. If not, there is a whole industry of things called rounding methods, which is a method to essentially take the matrix output by the semi-definite relaxation and try to round it to a solution of your original problem. Okay, this is called rounding problem.
You take the gradient of P, it's a polynomial.
Yes. Yeah.
And the squared gradient, where that's 0, will be a stationary.
Yes, exactly. Yeah.
You know that polynomial is non-negative. so you could search for the zeros of that.
Yes, I mean, in fact, I mean, there has been, yes, also a recent attempt to incorporate this idea of using the additional polynomial, which is the gradient, to improve this relaxation. That's a good, that's by Jiawang and Brunschrumpf. Yes, yeah. That's, so I actually wanted to mention maybe some applications. I didn't kind of talk about applications, but so one application of this approach is in dynamical systems and robotics. So whenever you have a polynomial dynamical system, so think of a vector x that obeys this differential equation. So dx over dt is equal to f of x, and f is a vector of polynomials. So one question that shows up a lot in dynamical systems and control theory is to certify stability of this dynamical system, meaning that you want to show that if you start in a certain initial, that if you start somewhere, then somehow the trajectories will all converge to the origin, somehow to the equilibrium. And the main way to actually show this is to find what we call a Lyapunov function, which is just an energy function that is non-negative everywhere, okay, and that decreases along the trajectories of my system. And one way to do this is to actually, so essentially, you see, I mean, if you're looking for polynomials energy functions, for polynomial Lyapunov functions, you can see that this is a non-negativity constraint, and this can also be written as a non-negativity constraint on the gradient of v, the inner product of the gradient of v with f of x, which is again still a polynomial. And so one way to try to search for such Lyapunov functions is using this sum of squares technology. Okay, and this actually has been used in robotics. I mean, so Ross Tedrake is a roboticist at MIT, and he's worked with his student Annie Majumdar and Amir Ali. They actually have used this, and they have some videos even on using this to control some of their robots. So, okay, and there are also many other applications. So in the optimal power flow problem, so DJ is going to talk about the optimal power flow, maybe not about this approach, but the approach based on sums of squares has certainly attracted a lot of attention recently in the community. In filter design, in electrical engineering, computer vision for the problem of triangulation, and also in the famous matrix completion problem, that's the general semi-definite programming. Okay. So if there are no more questions, maybe I will move on to something a bit different. So some of the recent work that I mentioned, this is with James Saunderson and Pablo Parillo, which is actually the problem of, now this is all very nice for polynomial problems, but what about if I have a non-polynomial problem, okay? So non-polynomial problems show up a lot specifically in information theory, so where we deal typically with, I mean, functions like the entropy function or the relative entropy function that involve the log, and these are inherently non-polynomial, okay? So the idea, what we wanted to do is to try to essentially find a good way, a principled way to approach these problems, again, using semi-definite programming. Okay. So in fact, I mean, solving these optimization problems, I mean, these are nice concave and convex optimization problems, but solving them numerically is not such an easy task. So one of the very famous convex optimization tools that was developed by Michael Grant and Stephen Boyd at Stanford, which is called CVX, and very useful for prototyping, which allows you to essentially just write optimization problems the way you write them on a paper. So essentially you write, I want to maximize the entropy of P subject to P being a probability distribution and some linear constraints. You can just write this. Okay, so essentially, so if you write this and you hit enter, then you'll actually get a warning from CVX. It will tell you that the entropy function is a function that we still cannot handle very well, because they have to essentially do a Taylor expansion of log to go back to polynomials, okay, to go back to things that they know how they can handle. Okay, so this is essentially a heuristic, so they don't have any convergence proofs, and in fact, so it works good in practice, but sometimes it fails, and it's actually quite slow quite slow for large problems. So our motivation to actually look at this problem a bit more in detail was not only to try to tackle this, but also to try to look at another class of problems for which there are actually no tools whatsoever that we are aware of, and this is to handle the case of the matrix logarithm. Okay, so we know what the log of a number is, so now let me talk about what the log of a matrix is. Okay, so if I take a matrix X with positive eigenvalues, the log of this matrix is just the log of, you take the log of the eigenvalues and you hit back by the unitary matrices that give you the diagonalization basis. Okay, and this log function on matrices happens to have very nice concavity properties. So essentially, you can show that the log of an average of two matrices is bigger in the positive semi-definite order than the average of the logs of the matrices. Okay, and this forms really the backbone of a very famous results used in quantum information theory, So essentially to prove that the von Neumann entropy, which is essentially the entropy of a quantum state, is a concave function in X, and that the quantum relative entropy, which is again a measure of distance between two quantum states, is a convex function. Okay, so and these are actually quite difficult results to prove. So this was first proved by Elliott Lieb and Mari Ruska in the 70s. So since then we have simpler proofs, but they're essentially much more difficult than just essentially differentiating twice and showing that it's not negative. It's not as easy as this. And so one of our motivation was to try to actually tackle such problems involving such functions using semi-definite programming. Okay, so what is our approach? Essentially, our approach was to use tools from approximation theory to get efficient approximations of log better than this Taylor approximation that doesn't work well for, in the approach that CVX does. And our approach is essentially based on just an integral representation of log. So we all know that the log is the integral of just 1 over x. So if you do a simple change of variables to move the interval to 0, 1, you can essentially show that the log is the integral of this rational function. So what is really nice about this integral representation is that the function inside the integrand is essentially a concave function of x for any fixed s. Okay, and so this is essentially a proof of concavity of log. And so one way to get an approximation is essentially just to use Gaussian quadrature on this integral representation. Okay, so if I use Gaussian quadrature, so essentially I sample the points s here from 0 to 1 according to the Gaussian nodes, to the Gaussian quadrature nodes, and I put the corresponding weights, I get a certain rational function that is an approximation of log that is much better than the Taylor approximation. Okay? And that is actually happens to coincide also with the Padilla approximant. Okay, if some people know in numerical analysis, which is essentially the rational approximant that agrees with the log with the maximum number of Taylor coefficients. Okay, and what is actually a very nice property of this approximation is that it's semi-definite representable. So you can handle this approximation using semi-definite programming. And the second remarkable fact about this is it actually works for the matrix logarithm. So if you put here a matrix X and a matrix and a matrix, this just works, and it's also semi-definite representable, so it preserves the concavity of our function. Okay, and so I mean this approximation is already quite nice, but we can even improve it better by using a well-known trick in numerical analysis, which is essentially if I take a matrix, I take its power with exponents that are smaller than 1 to bring it closer to the identity, and then I scale back. And so, okay, I'm not going to detail this, but essentially this still works for matrices, for quantum entropy, and it gives us, again, a much better approximation. So maybe I want to conclude just with just numerical examples where we tested this. So for very simple maximum entropy problems, so we compared it with the CVX successive approximation that I mentioned. So and for large problems, we see that our approach is actually much faster and gives us roughly the same accuracy. And so I want to also talk about one application in quantum information theory. So one key problem in quantum information theory is to measure what we call entanglement of a bipartite state. Okay, so you want to essentially minimize the quantum relative entropy from a certain state rho to the set of separable states. And so what we do is that we implemented this function in CVX that you can use, and so by solving this, by running this piece of code, you can solve this optimization problem, just in fact a relaxation of it. And what we get is something that is much faster than what people had designed a specific algorithm for this problem. Okay. So, so maybe I was a bit too quick at the end, but maybe just the takeaway message is this, maybe this figure, so is that semi-definite programming essentially is that, allows you to tackle now any arbitrary polynomial optimization problem. It's an active area of research to try to understand the quality of these approximations. And we also have ways, now we're developing new ways to deal with non-polynomial problems, essentially involving the log and entropy and so on, using tools from approximation theory. So I want to thank you all for your attention, and I'll be happy to answer any questions you have. Yes.
So the entropy problem that you mentioned is a convex optimization problem.
Yes, it is. Yeah.
So you could, in principle, design like a custom interior point method directly for that, rather than use CVX or something.
Yeah, you can.
So I'm just trying to understand if your approach would have an advantage as compared to that, or do you think it'll be more useful for non-convex problems involving language?
Yes, no, that's a good point. Yes, so I didn't mention this point because it was more for convex optimization experts. So So this is, it's true that these are all polynomial optimization problems, so we do have a barrier for these cones and so on, but we don't have, I mean, these solvers are not as mature as semi-definite programming solvers. I mean, they have been developed academically and so on, but they're not, I mean, we don't have the same quality of solvers as we do for semi-definite programming, so that's why we think this approach is still kind of useful. I mean, we do not have, I mean, CVX doesn't handle conic solvers for the exponential cone. So that's where we kind of that's where we, yeah. And for the non-convex thing, so this is still an ongoing area. I mean, this is all for convex problems, and we're still kind of working also on what if we have log but also non-convexity. So how can we deal with this? This is kind of an ongoing area of research.
But the semi-definite programming solvers, they are not based on some interior point as well?
They are based on interior point methods, yeah. But some, I mean, so the exponential cone solvers are also based on interior point methods, but semi-definite programming has a specific, very nice structure that allows, I mean, that makes these interior point methods. Any other questions? Yes, Matthew.
So the idea of expressing the log using quadrature,
yes,
in a sort of intuitive sense, is there a reason to think that it's optimal in any way? Is it the best representation?
So no, we actually do not know. I mean, you can show, okay, so now this will be a bit technical. So you can show that essentially the approximation we get using this, so essentially if you want accuracy epsilon, the size of the semi-definite programming we get is of size root log 1 over epsilon, and we do not know if this is the optimal kind of way to approximate the log. I mean, if there is a better SDP that can get a better approximation smaller than root log 1 over epsilon, we don't know if this is true. Any
All right. If there are no more questions, then let's thank once again Hamza.
Thanks a lot.